Now, coming to type 3, that is another category of question which will be asked in exam, and it is, if you are given a transfer function and you are asked to find the state model, then what will be your approach? See, in this topic or in this type, I am going to give you a lot of short tricks and short concept which will help you in solving gate exam and objective questions. But here I am not going to show you the conventional method of solving this type of questions, because conventional method is very complex, very lengthy. That I will take when I will start conventional classes. But for the time being, I am going to give you short tricks and concepts for objective questions. So let's start. Suppose we are given a transfer function in this form. This is one form of transfer function which is given to us. In common cases, we are going to see different types of transfer function, but here you just focus that transfer function given to us is of this type. Yes, in this lecture, for first 20-25 minutes, you just keep on listening what I am going to say. It may happen that you will get a little bit confused, but don't worry. You just listen what I am saying, and then we will take a question and all your doubts will be cleared. So what I am saying that let we have a transfer function which is in this form, and we are asked to represent it in state model. Then we very well know that total number of state variable will be equal to order of denominator. Total number of state variable. Total number of state variable will be equal to order of denominator. Order of denominator. Okay. Total number of state variable is equal to order of denominator. Now I want to represent it in state model. So I will write it like this. There will be 4 state variable. So x1 dot, x2 dot, x3 dot, x4 dot. 4 state variable. Here we will have matrix A. This I will fill later on. Here we have 4 state variable. Then here we will have matrix B. I will fill it later. Here we have input U. You can see output is YS, input is US. Now coming to output equation, let it be, take it as Y. Here we will get a matrix C, and again here we will have state variable. Now see carefully. I am going to give you a shortcut, very important shortcut. It will help you in solving this question within a minute. So how to write a matrix A? For first row, first two element will always be 0, 1. And after that, take as many 0 as you want. Here our state variables are 4. So after writing 0, 1, we only need 2 zeros. So for first row, the first two element will be always 0, 1, and then we will have number of zeros. For second row, we will shift this 1 towards right hand side. We are shifting this one towards right hand side. For third row, we will again shift this one towards right hand side. This is clear. For first row, the first two element will always be 0, 1, then right number of zeros. For second and third row, keep shifting 1 step towards the right hand side. Now come into the last. Now come into the last row. Very important. For this, what we have to do is that we have to take coefficients of denominator in reverse order, in reverse direction with opposite sign. We will take coefficients of denominator in reverse direction with the opposite sign. That is what we will get. We will get here minus a naught minus a1 minus a2 minus a3. This is coming out of this bracket. You can write it properly, but see what I am trying to say. The last row, for the last row, always take coefficients or denominator in reverse direction with opposite sign. So minus a naught, minus a1, minus a2, minus a3. Now coming to matrix B. Here put all terms 0 except term at last row, and here we will write k. This k is the gain of transfer function. This k will be the gain of transfer function. So for matrix B, all rows will be zeros except the last one, and here we will take gain of transfer function. Now coming to matrix C. Here what we have to do is that here we will take coefficients of numerator in reverse direction without opposite sign. Here we will take coefficient of numerator in reverse direction without opposite sign. So what we will get here? We will get here B naught, B1, B2, B3. So I hope this is clear. What I have told you. Okay. First see, this form of state model is known as controllable canonical form. This form of state model is known as controllable canonical form. So see what I have told you. We are having a transfer function which is in this form, and we are asked to find controllable canonical form. So we can write it in this way. For matrix A, for the first row, the first two element is 0, 1, and after that we have to take number of zeros. First two element of first row will be 0, 1, and then 0, 0 afterwards. Then for second and third, keep shifting 1 towards right hand side. For the last row, take coefficient of denominator in reverse order with opposite sign. For matrix B, all zeros will be 0, all rows will be 0. We will get term only in the last row, and that is the gain of the transfer function. For matrix C, take coefficients of numerator in reverse order without opposite sign. So this is our controllable canonical form. Just keep on listening what I am saying. Don't apply much brain. I will clear all your doubt. Don't worry. So next. So this was our controllable canonical form. Now if you are asked to find observable canonical form of same transfer function. This is the transfer function given, and now we are asked to find observable canonical form. then we have a short trick here. If we have controllable canonical form, then by taking its transpose, we can find observable canonical form. For matrix A of controllable canonical form, if we take its transpose, we will get matrix A of observable canonical form. And if we have matrix C in controllable canonical form, we can take its transpose, and it will become matrix B of observable canonical form. Similarly, if we have a matrix B in a controllable canonical form, and if we take its transpose, then we will get matrix C in observable canonical form. So let's see what we will get. We will first find a matrix A. We will first find matrix A. We will first find matrix A. We will first find matrix A. So take its transpose 0 1 0 0 0 1 0 0 0 0 1 0 0 0 1 0 0 0 0 1 0 0 0 1 minus A naught A1 A2 A3 minus A naught minus A1 minus A2 minus A3. So this is our A. Let's write it like this. It is our A. It is our A, matrix A in OCF, observable canonical form. We can write it in short, OCF, observable canonical form. Now let's see, if we want to find a matrix B of observable canonical form, then what we have to do? We have to take a transpose of matrix C. If we take transpose of matrix C, we will get B naught, B1, B2, B3. This will be our matrix B in observable canonical form. Now similarly, if we want to find matrix C in observable canonical form, what we have to do? We have to take transpose of matrix B. Transpose of matrix B. So we will get this. This will be our matrix C in observable canonical form. See, what we have done is that we have this transfer function. We know its CCF. Now, if we are asked to find OCF, then we can directly take a transpose of this. We can directly take transpose of this, and it will become this. It will become this. Okay, fine. See, the way I have taught you how to write CCF in this state model, in the same way I would have taught you how to write OCF of this transfer function in this state model. But you will get confused. Why to remember two things? Why to remember two shortcuts? We can remember one shortcut and then we can apply it for other one. Otherwise, if we remember both in the exam, we will forget both. So it's better that if a transfer function is given, find its CCF, and then if OCF is asked, do its transpose, you will get your answer. Do its transpose, you will get your answer. But if you want to memorize, but if you want to memorize how to write OCF, then see what I taught you here, that for first row, first two element is 0 1, then rest 0, then keep shifting 1 towards the right hand side. Similarly for OCF, the first two element of first column is 0 1 and then add 0 afterwards. Then for second and third column, keep shifting 1 towards the downward direction. And for the last row, take coefficients of denominator. For the last column, take coefficients of denominator in reverse order with opposite sign. So we will get this. What I told you, for first column, first two element is 0 1, then 0 0 afterwards. For second and third column, keep shifting 1 towards the downward direction. For the last column, take coefficients of denominator in reverse order with opposite sign. Now similarly, for if you want to see matrix B, then for matrix B, see what we are getting matrix B. For matrix B, write coefficients for matrix B. This one, this one, this one, this one. For in CCF, this was coming for matrix C, but for OCF, it will come for matrix B. For matrix B, write coefficients of numerator in reverse order without opposite sign. Now coming for matrix C. So the matrix which we were getting for here for matrix the value which we were getting for matrix B, that we will get for matrix C here. That is all columns will be here what I told you, all rows are 0 except the last one, and it will be the gain of transfer function. And for here all columns are 0 except the last one, and this will be the gain of transfer function. So see what I have taught you. I have taught you many shortcuts here. Suppose you are given a TF, means transfer function is given, and it should be in which form, that also I have showed you. It should be in this form. So what all we can do, we can write or we can represent this transfer function in state model in CCF form. The shortcut I have given you. Second, we can represent this transfer function in state model in OCF form. The shortcut I have given you. And the third one, I am telling you that you either remember this shortcut or you either remember this shortcut, and then you apply transpose as per the requirement. If you know this and this is asked, then you can apply transpose like this rule, and you can get result anywhere. You can come from this to this, you can come from this to this. Simple. See, two important, if I talk about CCF, then we can see that for last row, in the last row, we are getting the coefficients of denominator. For last row, we are getting the coefficient of denominator, and for OCF, in last column, we are getting the coefficient of denominator. These are some important points which will help you to recognize the state model. It will help you to recognize whether the state model is in CCF form or it is in OCF form. Similarly, the matrix where here B matrix will become C, and the C matrix is becoming B matrix. B matrix means here 000K, where we are getting it C matrix, there we will getting it in B matrix, and this B0, B1, B2, B3 in OCF we are getting it in B matrix, but here we were getting it in C matrix. Okay. So the third one is CCF and OCF are interchangeable provided you understand this concept. Okay. See now, you may say that, sir, you are telling one thing, that we are given a transfer function, and for the same transfer function we are getting two state model. One is in CCF form and one is in OCF form. Why it is so? Why it is so? Then it is because I will give you more clarity on this in coming time. But here you just remember that for same transfer function we are getting two representation of state model, because we are taking state variable in different order. That is, as we will change the order of state variable, as we will change the order of state variable, we will get different representation of state model. We can get CCF as well as we can get OCF by changing the order of state variable. You will remember that we have looked the same, we have understood the same thing in SFG also, in signal flow graph also, that when we were changing the order of state variable, then we were getting different state model. Same is applicable here. If we change the order of state variable, we will get different representation of state model for the same transfer function. For the same transfer function. And how we are taking the order to get this CCF and OCF, that I will teach you once I take the conventional classes. Once I take the conventional classes. Now, let's solve a problem. Let's solve a problem, and then things will be much clear for you. Yes. Now, let's solve a question, and now things will start getting clear to you if there's some doubt in your mind. But I have given you the concept in a very basic way, and I think that most part would have been clear. But still, if there's some doubt, then we can see here. Suppose we have a question, it state matrix of system with transfer function. This it is telling that you are given a transfer function and you have to find it state model. Basically, we have to find a matrix A. In most of the time, you will be asked to find matrix A only. B and C seldom are asked. So see, for this type of questions, means for category 3 type of questions, that is, if you are given a transfer function and you are asked to find the state model, then we will always apply reverse engineering. That is, we will always find answer from the options. We will do reverse engineering. So what we have to do first is, if I write it, step 1. Step 1, we have to find out whether the given option is in OCF or it is in CCF. So step 1, we have to check these options and see that whether it is in OCF or it is in CCF. And after covering it, if we are able to identify it, it is this step is very important. If you are able to identify it, then you can easily apply the short tricks which I have conveyed you, of how we find matrix A in CCF and how we find matrix A in OCF, and then you can easily get your answer. So let's see. Yes, one doubt you will have. You can say that, sir, if both OCF model and if both the OCF option and CCF option are available in the option, then what we will do? Then don't worry, such combination will never be asked. You will never find a four options in which in one option you will find OCF model, and in other you will find CCF model. It will never be asked. And why can't it be asked? That also I will give you with reason, but wait for some time. So let's see. So here we can see first row, first two element 0, 1. First row, first two element 0, 1, 0, 1, 0, 1. Then 1 is getting shifted. And then, so from here we can see that it is CCF. It is CCF. It is CCF. Now, suppose we take another question to clear your doubt. Here also the transfer function is same, s3 6x square 5s plus 4 s3. Anyway, चलो ये कोएफिशिएंट चेंज कर देते हैं, चलो ठीक है। 6 के जगह 10 कर देते हैं, 5 के जगह 8 कर देंगे, एंड यहाँ 5 के जगह 4, तो यहाँ ये let's suppose we are having this coefficient. We can take this coefficients also, because mainly we are learning concepts here, so we can take this coefficient. Let's take this coefficient only, because options are in this coefficient only. Don't get confused. Means I am trying to tell you that the form of transfer function is same, only the coefficients are different. But basically what I am trying to teach you, you learn that. So I told you the first step is always to try to figure out whether the state model is in OCF or CCF. That we found out here that the model is in form of CCF. Now see, here we can see that 0 1 0 1 0 1 0 1 is in the first column. Then 1 is getting shifted. 1 is getting shifted. It means it is in OCF. It is in OCF. It is in OCF. So this is the first step, very important step. Then coming to the second step, and that is to identify the exact answer. So I told you that for the last row, we take coefficients of denominator in reverse order with negative polarity. So see, only option D I think is matching, -5, -8, -10. This is matching. Okay, I hope it is clear. Now coming to this, in this I told you that we will take coefficients of denominator in reverse order with a negative with opposite sign, and it will come in the last column. So see, yes, okay. Here the options are different. Here options are different. Here options are based on the transfer function of above transfer function. So don't take this transfer function. Let's assume we are having transfer function this. What we are having? 10s square, 10s square, 8s plus 5, 8s plus 5. Okay, let's assume this is our transfer function. Don't assume this. And this transfer function is same. And see, we in one transfer function we are representing it in OCF form, and and for the same transfer function in another we are represented in another form, that is in CCF form. That is, same transfer function is represented in two form, one in CCF and other in OCF. And it is because I told you that if we will change the order in which we are taking the state variable, then we will get different forms of same transfer function. So here we will, what we will do, we will take coefficients of denominator in reverse direction with opposite sign. So -5, -8, -10. This will be our answer. I hope it is clear. Simple. I hope it is clear. And all your doubt also must have been cleared now, that what all are our short tricks and in which way question will be asked from you, and what steps you have to follow. First you have to identify from the solution, is it OCF or CCF, and then you know the shortcut of representing a transfer function in OCF and CCF. apply the shortcut and you will get the result. Here, one more thing. Uh, Suppose, as I was telling you, that you try to memorize one shortcut and other shortcut you can apply at the exam time only by just knowing that we can find OCF by taking transpose of this, or we can find CCF by taking transpose of this. Suppose we are given this question, we found out that it is in OCF or CCF. This you have to figure it out. Here there is no shortcut. This you have to figure it out, that whether the given options are in OCF or CCF. Suppose you found that it is in CCF, but you don't know how to represent transfer function in CCF, but you know that how you represent transfer function in OCF. Then you represent this transfer function in OCF, take its transpose, you will get the result. Fine. Similarly here, first you have to identify whether it is OCF or CCF. If you have identified that it is OCF, but you don't know how to represent transfer function in OCF, represent it in CCF. You must be knowing one out of them, and then take transpose and you will get OCF. So I hope this is clear. Now student, come here. I am going to give you a very important point, very important difference between transfer function and state model. It is very important for your objective point of view, as well as for the interview point of view, as well as for your understanding of the subject. So see, I am writing two statement. Transfer function. Transfer function is unique for a system. Is unique for a system. Transfer function is unique for a system. State model is not unique. State model is not unique for a system. This is very important statement that I am giving you. Transfer function is unique for a system, but state model is not unique for a system. You will say why. Then see, I am going to explain it. First, when we were discussing, when we were discussing, when we were discussing SFZ, there we saw that as we changed order of state variable, as we changed order of state variable, our state model changed. Our state model changed. So for same SFZ, we were getting two state model, but it will never happen for transfer function. For transfer function, for one SFG, you will get only one transfer function. But here, when we were changing the order of the state variable, our state model was changing. Then second example, this is the recent thing which we have studied. That is, for the same transfer function, we were getting different forms of state equation. One form we were calling it as CCF, and the other form we were calling it as OCF. And these two different forms we were getting because we changed the order of state variable. That's why it is said that state model is not unique. Now coming to your question that I was discussing here, that you may ask that, sir, if we are given one option of OCF and one option of CCF in the same equation, then is it possible? I told you not possible. See why. Suppose there are two brothers, Ram and Shyam. Ram and Shyam. Shyam's pet name is Sonu. Shyam's pet name is Sonu. Now, if you are given a question, what is the, you are asked a question, what is name of Ram's brother? You are asked a question, what is the name of Ram's brother? Options are Shyam, Sonu, Monu, Bhonu. Anything you can take. Then see, what is the name of Ram's brother? So, some will say Shyam, some will say Sonu, because Shyam and Sonu represents the same person. So, this type of questions will never be asked because it is illogical question. So you will never be asked a question in which CCF and OCF will be both will be given to you. So don't worry about this. So this was about the CCF. This was about the OCF. That for same transfer function by varying the state variable, sometimes we will get sometime CCF, we will get sometime OCF. How we are getting that we will deal in the conventional course. Then how I have given you the shortcut of writing CCF, to write the state model of CCF, to write the state model of OCF. And if you know if you know CCF, then how to find OCF and vice versa. And then we solved a question in which I told you that apply reverse engineering, find the answer by going through the solution. First find whether it is CCF or OCF, and once you are able to figure it out, just apply the shortcut, you will get the answer. Then I gave you a very important statement that transfer function is unique, state model is not unique, because by varying state variable we are getting different state model. So I hope it is clear to you. Now, coming to case 3, it is another form of canonical form. It is called diagonal canonical form. So, we have a transfer function like this. For diagonal canonical form, transfer function should have two prerequisites. Transfer function should have two prerequisites for representing it in diagonal canonical form. The first prerequisite is that order of each pole should be 1. Order of each pole should be 1. See here we can see that order of each pole is 1. And the second prerequisite is that there shouldn't be any repeated roots. No repeated, no repeated poles, no repeated poles. Here we can see there are no repeated poles. See now, if we want to represent it as a state model, if we want to represent it as a state model, so how we can represent it? This one is that suppose we have taken partial fraction of this transfer function, then suppose we get this result. Partial fraction is done. Partial fraction is done. And we got this result. We will come into it later. Little later. So now we have to represent this transfer function. This transfer function is having two prerequisites, that is order of each pole is 1 and there are no repeated poles. So this satisfies the condition of diagonal canonical form. So now we will write it in state model. So for state model, I am writing only matrix A, B, C. I am not writing the complete equation because I think now you are accustomed with it. So for diagonal canonical form, it will be represented as this. We will get elements only at diagonal. and rest elements will be 0. That is, diagonal elements are not non-zero, other elements are 0. This will be our matrix A. This will be our matrix A. This will be our matrix A. Now suppose B is this, assume B is this K1, K2, K3. B is this K1, K2, K3, and suppose C is L1, L2, L3. See, what will be exact B, what will be exact C? This we will see when we will take up in conventional classes. Here, the main thing is to how to write the matrix A. Matrix B and C are not important, but from matrix C, B and C, I am going to give you a concept. So, assume B is this, C is this. Now, what we will get is K1 L1 is equal to this. After doing partial fraction, we get this result. So its value is C1. K1 L1 will be equal to C1. K2 L2 is equal to C2. K3 L3 is equal to C3. See, by this thing, what I am trying to teach you is that from here also we can see that state model is not unique, because by varying values of k, by varying values of k1, k2, k3 or l1, l2, l3, we will get different state equations. We will get different state equations. For example, if I take, suppose C1 is 5. Then see what all are the possibilities for getting C1. If I write K1 L1, K1 L1, 1 cross 5 is 5, or 5 cross 1 is 5, 2.5 cross 2 is 5, 2 cross 2.5 is 5. So what we can see that for one value of C1, there are 4 possibilities. That is, we will get 4 type of state equation. So I'm trying to teach you that why this our state equation is not unique. We saw it in SFG, we saw it in CCF and OCF. We are seeing it in DCF also, diagonal canonical form. We also call it as uh, also call it as, let's suppose, DCF. We call it as DCF. So this was all about DCF. Now, students, coming to case 4, Jordan canonical form. It is another type of canonical form. So what the before this we have seen CCF, OCF, DCF. Now we are seeing JCF. So the prerequisites for DCF was poles shouldn't be repeated, but in case poles are repeated, poles are repeated, but in case poles are repeated, then we will get JCF. For example, if we can take case 1, let poles are, what you will take? P1, I will take it as okay, let's take P only, because in DCF we represented pole in P, so it will be easy for you to understand it. P1, P1, P2. Let we have these three. Let we have these three poles in which P1 is repeated two times. In which P1 is repeated two times. Then what will be our matrix A? Then what will be our matrix A in JCF? So we can write our matrix A. We can write our matrix A for understanding purpose. Let's take it as minus P1, minus P1, minus P1, because I want to correlate it with our this DCF. Here, if we will take it, equate each pole with 0, then we will get poles as minus P1, minus P2, minus P3. So let's poles are minus P1, minus P1, minus P2. So here we will get minus P1, 1, 0. Here it will come 0, minus P1, 0, 0, 0, minus P2. This is the way of representing poles in JCF, and this is our matrix A. This is our matrix A. This is known as Jordan block 1. This is known as Jordan block 1. This is known as Jordan block 2. This is known as Jordan block 2. So what is the uniqueness? Minus P1, minus P1, 1, 0. This 1, 0 can interchange. Sometimes you may find 1 here, 0 here, and sometimes in question you can find 1 here, 0 here. So don't get confused, but you should focus on this type of combination, poles 1, 0, 1, 0. And here the another pole is this. Okay. Now coming to case 2. Now coming to case 2. Suppose we have a poles like this. P2 is repeated now. P2 is repeated now. So now if we want to represent A matrix, if we want to represent A matrix, we will represent it as minus P1, 0, 0, okay, 0, minus P2, 1, 0, 0, minus P2. So here again we can see this is our Jordan block 1. This is our Jordan block 1, and this is our Jordan block 2. This is our Jordan block 2. Easy. 1, 0. Repeated poles 1, 0. Easy. Now if we take one more case, case 3. Suppose all poles are repeated. Suppose all poles are repeated. Then what will be our matrix A? Then what will be our matrix A? It will be minus P1, minus P1, minus P1, 1 0 0 1 0 0. See, very easy. Consider this block. Consider this block. So this is our JCF. So this is our JCF. You need to identify canonical forms. You need to identify canonical forms. What we have seen four types of canonical form. CCF, we have seen OCF, we have seen JC, no, um, DCF, we have seen, and JCF, we have seen. So if you are given a transfer function, now see, another important concept which will be useful for you. See, if you are given a transfer function in this form, so looking at this form, you can easily say that order of each pole is 1, no poles are repeated. Okay, then it's a DCF, it's a DCF. You can find out the options and you can take it. Now, if there are some repeated poles, you will say that it is JCF. You will again find the options and you can take it. But see, if we will expand this denominator, then we will get a transfer function, something similar to this. Okay, if we will expand our DCF, not DCF, if we will expand any transfer function, then we will get in this form, and from this form we cannot say that it is in DCF or it is in JCF, because we have to do some calculations. We have to apply quadratic equation, then we can find poles. Here it's a fourth order denominator. It will be very complex, so you cannot easily find out that whether the order of the roots are 1, whether roots are getting repeated or not. So what is the best way of dealing with the questions of transfer functions in exam? So first of all, I told you that whenever you get a question to find transfer function, to find a state model from a transfer function, then always apply reverse engineering, look at the options, then find the solution. And always try to uh, look at the option in this priority. This will be your priority. This will be your priority. Always try to find out in the option that whether your options is in CCF form. If yes, then you know the shortcut. If not, then go for OCF. Find out is it is in OCF form. If yes, you have the shortcut. If no, then see if it is in a DCF form. The options are is in DCF form. How you can get? The only diagonal elements are non-zero, rest elements are 0. If yes, okay. If not, then you will come for JCF. For JCF, it is the last option basically. So यहाँ तक पहुँचते आपको आंसर मिल ही जाएगा, या नहीं मिलेगा तो यहाँ तो आपको मिलना ही मिलना है. But it's still the form of JCF is this: poles 1 0, poles 1 0, 1 0, 1 0. So this was all about your different types of canonical form. I hope now it is easy for you. You have understood the things, and you have also understood how to approach a question. How to approach a question is very important. If you are if the transfer form, if the transfer function is given in the form of DCF, that is you can see that there are no poles repeated, then you can easily go for DCF. You will find the option also. If the transfer function is in the form where you can easily find that the poles are repeated, then go for JCF. You will find that in the options also easily. But if you are given a general transfer function, then it will be very difficult for you to identify that whether it is DCF or whether it is JCF. So go with this priority. Go for CCF first, go for OCF first, go for DCF first, then go for JCF first. I hope that you will appreciate this effort. Now, coming to type 4, that is another type of questions that may be asked in exam, and that is if you are asked to represent differential equation as a state model, then there's a very easy and shorter concept, or you may say trick, that I'm going to give. Always convert differential equation into a transfer function. Always convert, always convert differential equation, differential equation into transfer function. Means you will be given a differential equation and you will be asked to find its state model. So always convert that differential equation into a transfer function, and from transfer function how we get the state model, that we have discussed in details. So let's take some example, then it will be clear for you. Suppose we have this question. Suppose we are having this question, find a state model for following differential equation. So find its transfer function. For finding its transfer function, we have to convert it into S domain by taking Laplace equation, that I think that you know after completing the signals and system classes. So I will write it directly. So y of s, it will become s cube. It will become 5s square. It will become 8s plus 10 is equal to 11 us. So our transfer function will be something like ys by us is equal to 11 by s cube plus 5s square plus 8s plus 10. So it's a general form of transfer function. I will represent it in a state model by considering CCF, that is controllable canonical form. So for CCF, I will write matrix A. We know it very well. Order is 3, okay. 0, 1, 0, 0, 0, 1. Then I will get minus 10, minus 8, minus 5. This will be my matrix A. My matrix B will be 0, 0, 11. 11 is this. 11 is this. Gain. Gain will come here. Then come into matrix C. Come into matrix C. Matrix C will be 1, 0, 0, 0, because here there are no 0. Here there are no 0 term. No 0 term. So it will come 1, 0, 0. So now we have A, B, C. Now how to represent it into state equation, output equation, you know it very well. So this is the way how we can convert differential equation first into transfer function, and from transfer function into state model. Now let's take another example. I have taken 3 different form of differential equation, and after solving this 3 different form, you can solve any questions on differential equation. There will be no problem to it. So again here, converting into uh, transfer function s cube 0 s square. See, here you can see that one term is missing. So it is 0 s square plus 8s plus 10 is equal to 11 us. Now our transfer function will be ys by US 11 by S cube 0s square 8s plus 10. This both this question and this question is same. Only thing is that this term is missing. This term is missing in this question. So now what will be my matrix A? Again CCF. I will take it in CCF 0 1 0 0 0 1. Take it minus 10 minus 8, and here I will get 0. So this is very important. Always always be very careful that all terms are present or not. The question framer plays very smartly. So be very careful, be very attentive. See, the one basic mantra of attempting questions in competitive exam, yes, there's a factor of time, no doubt, but always be attentive while reading a question. If you will think that I will read a question in hurry and I will save time, then you are committing a mistake, because you will miss some important thing, and then you will follow wrong directions and you will commit silly mistakes. So always give time in study in reading the question, what the question is asking from you, then start your solution. Okay, now coming to third type of differential equation. Okay, well, here B will be same. B will be y 0 0 11 you will get, and here C there is no 0, so 1 0 0 you will get. Now in this question I have taken 0, so now you will so now from here you can see that how I will write matrix C also. So I will write directly here transfer function S plus 3 S square 3s plus 4. Okay, so what will be my matrix A? My matrix A will be 0 1. It is order 2. Number of state variable is equal to number of is equal to order of differential equation. um, so it will be so let me write this also in case. Yeah, order of differential equation is equal to number of state variable. Number of state variable, important. So now order is 2, number of state variable will be 2, so 0 1, and here I will write minus 4 minus 3. Now B C, what will be the gain? 1, so B is 0 1. Now C take it in coefficient of numerator in reverse direction without opposite sign, so it will be 3, it will be 1. So by this 3 examples, I think now you are comfortable that if a differential equation is given, how you will convert it into transfer function, how will you convert it into state model. Now let's take some general questions. It will clear your doubt if there is any. Yes, see, a very important pattern. See, if you are given a state model and then you are asked to find transfer function. If you are given a state model and you are asked to find transfer function, then what will be your approach? Always focus matrix A. Always focus matrix A. So matrix A, what it is given? 0 1. 0 1. That is the first row, first two element is 0 1. So we very well know that it is in CCF form. अगर ये 0 1 यहाँ फर्स्ट कॉलम में होता, फर्स्ट कॉलम में मेरा 0 1 होता, तो हम समझ जाते कि ये मेरा OCF फॉर्म में, लेकिन यहाँ पे ये CCF form में. तो CCF form में we know very well how to write the how to get the transfer function. See, first take in B. This represent gain 2 2 2 2. Okay, it is same everywhere. Everywhere. Now this 6 5, no. Yes, 5 and 6. 5 will come here, 6 will come here, and if we take about denominator, 2 will come here with opposite sign, 1 will come here with it. So this is the equation. So now if you are given a state model and if you are asked to find the transfer function, then always focus one, see in which form it is given. If it is in CCF, 0 1 will be here. If it is OCF, 0 1 will be here. If it is in DCF, diagonal canonical form, then you will get P1 and P2. That is, you will always get elements, non-diagonal elements will be non-zero, rest will be 0. And similarly, if you are given a JCF, a Jordan canonical form, then you will get something like this. You will get something like this. And then after you are able to conclude that it is in which form, you can easily find the transfer function. Now let's see another question. State matrix for transfer function. Transfer function is given. We have to find the matrix A. Then here we can very well see that poles are repeated. Poles are repeated means Jordan canonical form. It should be Jordan canonical form. So let's see the option. See here -3, -3, -4, -5 means it is a kind of a diagonal canonical form, which is also not right because in diagonal canonical form, my poles will never be repeated. Here you can see, here you can see that poles are repeated. Here also you can see, and here also you can see poles are repeated. So this also option will be wrong, but it is a kind of DCF. The examiner is trying to convey you that it's a DCF. Now coming to here, see 0 1, this, it is in the form of CCF, and see here it is in the form of OCF. But what I told you, first we will refer the transfer function. If we are able to conclude that transfer function is a kind of DCF or it is a kind of JCF, means if there are no repeated poles and we are able to find individual poles, then we can say that it is a DCF. But if they are repeated poles, then we will say that it is a JCF. But if it was given in a general form, then we could have written it as CCF or OCF. So the option left is this. See, this is the Jordan block. This is the Jordan block. This is the Jordan block. So students, I hope that now you are comfortable with, if you are given a transfer function, then how you can convert it into a state model. If you are given a differential equation, then how you can convert it into a state model. If you are given a state model, then how you can find the transfer function. This question is also very important. Now, coming to type 5. In this type, we are going to look into number of things. First is the how to find a solution of a state variable, then how to find a state transition matrix, how to calculate transfer function, and then how we can calculate output equation also. So this type is very important, very important for GATE point of view. If you will see previous year questions, then you will find number of questions which has come from this domain. So we are going to learn many concepts, many short tricks here, and I am also going to remove a number of misconceptions which must be in your mind regarding some of the points which we will discuss here. So just listen to it by open mind. Don't keep any baggage in your mind. Just listen what I am going to brief you here, and then all your concepts will be cleared. So let start with the first one, that is a solution of a state variable. So suppose we have a state equation like it. Suppose we have something like let's change the color. Suppose we are having this x1t, x2t. Let's consider we have a matrix A, B, C, D, x1t, x2t. Let we have a B matrix and then ut. So now see, the solution of state variable, we are going to discuss it by two methods. We have two methods of finding the solution of state variable. This is our method one, and after this I will also show you method two, and then it will be up to you in which method you are comfortable and that you can apply in exam. In this method you will see that you don't even require any knowledge of state space also. You just require a basic knowledge of matrices, and you will get the answer. See how we can get it. Let we expand it. After expanding we will get something like this: x1 dot t, a x1 t, b x2 t, e ut, and expanding x2 dot t, we will get c x1 t, d x2 t, f u t. Suppose initial condition is also given to us. Suppose initial condition is also given to us: x10 minus x20 minus. These are the initial conditions which is already given to us. It is already given to us. Now see what will be our next step. Suppose we take Laplace transform of both this equation. What we will get? We will get something like s x1 s minus initial condition. Here we will get something like this: x2 s u of s. Suppose it is equation 1. Now applying a Laplace transform in the second one. No, the dot will not be here. Dot will be dot will not be here. x2s. Yes, then the initial condition. Then initial condition. Initial condition. Initial condition. Yes, this is our equation 2. Now you can see what we are having here. We are having two equations, equation 1 and 2, and two unknowns. x1s and x2s are two unknowns. Means we have two equation, two unknowns. We can easily find out the value of x1 and x2s. So what we have got now? By solving these two equation, we will get x1s and x2s. If we will take a inverse Laplace transform of it, we will get x1t and x2t. And this x1t and x2t are our state variable. So this is the first method of finding state variable, where you don't require any specific knowledge of state space. You just require a basic knowledge of matrix expansion. So now let's discuss method 2 also. Now coming to method 2. Method 2. Now suppose you want to solve directly in the matrix form, then you can apply method 2. See, I will take an example and I will solve that example using method 1 and 2. So don't worry. So I told you that if you want to solve to find the state variable directly in matrix form, then what you can do? Suppose we have a state equation like this. Dot t x of t. A is also a matrix. All are in matrices form. B is also in matrix, and ut. Suppose we have initial condition also. Suppose we have initial condition also. Initial condition is also given. Initial condition is also given. Now, if we will take a Laplace transform, then what we will get? See, we are not expanding it. We are not taking it out of matrices. We are, or everything which we are doing is inside matrix only. So we will get S x1s. Don't write x1, because here I have not taken x1 or x2. So let's write it simple as x of s minus is initial condition, minus initial condition. It is inside a matrix only. Then here we will get x of s. Here we will get u of s. All are inside matrices only. Now we will do some shuffling. We will do some shuffling, and then we will get something like this. Take it in LHS side. Take the initial condition in RHS side. Yes. See, this one we can write it like this. It is a property of matrices only. We can write it like this. No. Let's take it common. X of s si minus a 0 minus. Then finally, what we will get? We will get something like this. Si minus a inverse initial condition. Keep in mind, this all are in matrices. I told you that I will solve a example. If you are having any doubt, then it will be solved there. It will be removed there. Doubts can be removed. Doubts cannot be solved. Okay. So this is something which we are getting. Suppose if we want to expand it little further, so we can take it in this form. X1 this X1s, X2s. This will be same, that initial conditions are this. U1s, U2s. So this is what we will get. This is what we will get. Now see, yes, this all are in S domain. This is all are in S domain. You will say that, sir, how we can find state variable. Yes, मतलब you can say that, sir, we have found state variable in S domain, but we want it in time domain also. So I will show you that how we will convert it from S domain to time domain. Don't worry. But before that, see, here we have got a new term, a new unique type of term we have got, that is Si minus a whole inverse. This is known as STM. This is known as STM, that is state transition matrix. That is state transition matrix. So I will take this conversion from S domain to T domain later on. First, we will discuss about the STM. First, we will discuss about the state transition matrix. Now, we saw that Si minus A, Si minus A inverse, Si minus A inverse is known as STM. That is state transition matrix. That is state transition matrix. Now, if we take inverse Laplace transform of it, if we will take inverse Laplace transform of it, if we will take inverse Laplace transform of it, then also we will get STM, that is state transition matrix. So we can say that this state transition matrix is in S domain, is in S domain, is in S domain, and this state transition matrix is in time domain, is in time domain, is in time domain. Now, let's see an example. Now, let's see an example. Suppose we are given a matrix. Suppose we are given a matrix and we are asked to find its STM. Find STM. Find STM. So what will be our approach? We have to find Si minus A first. These are basic matrices properties which you must be knowing it very well. So here nothing I have to teach. Just see it. Si minus A. Si minus A. Si minus A. Now what we will get? We will get something like this. Now if we will take its inverse. Now if we will take its inverse, so we know that it will be 1 by determinant. This two will interchange, so it will come like this only. And in this two, there will be sign change. There will be sign change. So finally, what we will get? finally we will get something like this. Finally we will get something like this. 1 by s minus 2, 0, 0, 1 by s minus 2. So this is STM. So this is STM in S domain. So this is STM in S domain. Now if we will take inverse Laplace transform of it. Now if we will get take inverse Laplace transform of it, then we will get something like this and ut ut. So this is STM in time domain. This is STM in time domain. So it is easy. What we saw that. So this one is easy. What we saw that SI minus A inverse is known as the state transition matrix in S domain, and if we will take inverse Laplace transform of it, then it will become STM in time domain. Then we took an example. We found SI minus A, then we found SI minus A inverse, and then we got it Laplace inverse Laplace transform, and this is these two are our final STM in S domain and in T domain respectively. Now coming to next important topic, and that is properties of STM. This is important because sometimes direct questions are asked from properties. So let's see. First property is 5 to the power kt. It will become 5 kt. Second property, it is the extension of this only. Suppose in place of k we will take minus 1. So what we will get? We will get 5 minus t. Easy. Now coming to third property, d phi t by dt at t is equal to 0. We will get matrix A. We will get matrix A. Then coming to fourth property, phi t minus t naught is equal to product of phi t into phi t naught. Now suppose, now see, we are taking in terms of phi t, phi t, phi t. We can also take the same thing in terms of e to the power at. We will get the result same. So I am not writing it. You can write it in your notebook, because phi t and e to the power at denote the same thing, that is STM. So see, this property is very important for exam. Phi to the power kt, it will be equal to phi kt, and this property is very important for exam. That is, if we take differentiation of STM and then put t is equal to 0, then we will get matrix A. We will solve questions on these two properties. You will see it. So keep it in mind. These two properties are important. So now see, what we saw that if we are given a state equation, if we are given a state equation, something like this. If we are given a state equation, something like this, and if we are asked to find its solution, and we are asked to find its solution, find its solution. So what we got was, we got something like this. We got something like this. Si minus A inverse matrix B and u of s. Now see, if we will take a inverse Laplace transform of both LHS and RHS, inverse Laplace transform. If we will take inverse Laplace transform, then we will get something like this. It will be represented as phi t, and this is the initial condition. So it will be remain like this. Now here we will write it like this. Si minus A. This is in matrices. So be careful. B. So can we write it like this? We are taking inverse Laplace transform of it. Now see, if we further want to expand it, then what we will get? We will get something like this. See, this part is in S domain. This part is in S domain. This part is in S domain. B is a matrix, and this part is also in S domain. This part is also in S domain. So we have learned in signaling system that when we take multiplication in S domain, then we get convolution in time domain. When we take multiplication in S domain, then we get convolution in time domain. So we can write it like this. Very important. See, it is very important, very important. Please see. So we will get what? Phi t convolution matrix B, and here we will get ut. Here we will get ut. See, so this will be the final solution which we will get. This is the final solution which we will get. We can represent it like this also. Xt phi t initial condition inverse Laplace transform of Si minus A inverse B and Us. And if we will further expand it, then we will get it like this. In this we can see that all the terms are in time domain, and here this was in S domain, and when we were converting it from S domain to time domain, then we have to take convolution, because this is in S domain, this is in S domain, and we know that multiplication in S domain comes to convolution in time domain. Now see, while solving problem, which is the best way to proceed? See, next I am going to solve a problem in which I will solve that problem using both method 1 and method 2. And there also I will show you how to deal with this term, that is how to solve this term in an easy way. But still, if we want to discuss it here, then see what we have first. How we can solve it, if we take it as a case 1, then see this is this STM. We can find Si minus A inverse, and we will get an STM in S domain. Fine. Then this is B, matrix B, and then this is input, it is in matrix. So we can first solve all this. We can take multiplication of all this. We can take multiplication of all this by applying product rule of matrices, and then we can take its inverse Laplace transform, so that we will get all the terms in phi t. See, first that is so first step is like this. Second step is that take phi t, means convert this STM. After solving Si minus A inverse, you will get an STM in S domain. Convert it into time domain. Okay. Then take convolution of matrix B and ut. This two say this term will be separate. Here what you will do, here you will take Si minus A inverse, you will get STM in S domain, that you will convert in time domain by taking inverse Laplace transform, and you will get phi t. Okay. Then you will apply product rule here in matrix B and matrix Us, and you will get a term in matrices, and then convert it also in time domain by taking inverse Laplace transform. So you will get this term. You will get this term. Here also you can see that we are having matrix B, and we have taken ut in time domain. Now we will take product of this, applying product rule of matrices, and you will get one term. So this is our first term, and This is our first term, and this is our second terms. This is our second term, and then we will take convolution of both, but here you will find it difficult because solving convolution becomes a tedious task most of the time. So I would prefer not to go for this method. The simple method is that keep STM in S domain only. You have matrix B, keep input in S domain only, apply product rule here. You will get a single matrix, then take its inverse Laplace transform. Rather than converting this in time domain and getting this, and then solving this, and then getting it in time domain and taking convolution. So be careful. So I will solve an example, so things will be clear there. Now let's take an example. We will solve an example, and I will solve it by both way, by method 1 as well as method 2, so that it will be clear to you. So let's suppose we have an state equation like this: 1 1 x 1 1 u, y is 1 1 x, and initial conditions are 1 and 0. You are asked to find state variable and output. You are asked to find a state variable and output. So let's see. We will start with method 1. So if we want to expand it, so what we will get? We will get something like this: x1 dot t is equal to x1 t plus u t. Now taking it is now take the Laplace transform. Now take Laplace transform. We will get this with the initial condition, then this, then this. Now this minus 1 by s plus 1. S plus 1 by this. It will come s plus 1 by s minus 1. This is our x1t. This is our x1t. This side s minus 1, s plus 1 by this. If we will take partial fraction of it, let's see what we will get. We will get s plus 1 a s minus 1 plus b s. If s is 0, a is equal to 1. If s is 1, then b is equal to 0. If s is 1, then b is equal to 0. So finally, what we will get? We will get as this: x1s is equal to 2 by s minus 1 plus 1 by s. Now if we will convert it into x1t, so we will take inverse Laplace transform of this, and this we will get 2 e to the power t plus 1 u t. This is x1t. this is x1 t, this is x1 t, and this is x1s, this is x1s. Okay, now coming to x2s, so we can write x2 dot t is equal to x1 t x2 t plus ut. Now we will take a Laplace transform of this. So we will get this. Initial condition is 0. x1s. x1s is 2 by s minus 1. 2 by s minus 1 plus 1 by s, or s plus 1 by s minus 1. s plus 1 by s minus s plus 1 by s minus s. This s will come here. S plus 1 by s minus 1. This will become x2s plus 1 by s. So x2s will become s minus 1. And here what we will get? We will get s plus 1 plus s minus 1 by s minus 1 whole square. So we will get 2 by s minus 1 whole square. So we will get x2t is equal to 2t e to the power t ut. This we are getting x2t. This we are getting x2t. Now see, we have to find output. What is the output? If here we will expand it, we will get yt is equal to x1t plus x2t. So now we can write it like this. Yt is equal to x1t plus x2t. I hope this my handwriting say I am writing in a very rough manner. So keep listening to me. The notes which you will get of mine, there everything will be written very properly. That too in a neat and clean handwriting. So you will get yt is equal to 2 e to the power t, 2 e to the power t plus 1 ut, and here 2t, 2t e to the power t this. Hmm. A will be minus 1. A will be minus 1. A will be minus 1. So here we will get, here we will get minus. Here also we will get minus. Here it is okay. Here we will get minus 2 e to the power t minus 1 plus 2 t t. So this is our yt. So this is our yt which we are getting from method 1, in which we didn't require any knowledge of state space. We just use the basic concept of matrices and we expanded it, and then we found yt. Okay, so now let's see, let's solve this method problem by method 2. In method 2, we saw that what we were getting. We were getting state variable is Si minus A inverse x of 0 minus plus Si minus A inverse B U of S. Okay. Now let's see. Let's find. We will first find. We will do it in two parts. First, we will find out this. Then we will find out this. Then we will add on. So anyway, we have to find STM, as STM is in both. So Si minus A, Si minus A, 0S, A, 1011. So this we can find, right? S minus 1, 0, minus 1, S minus 1. If we will take its inverse, if we will take its inverse, what we will find, what we will get? We will get 1 by S minus 1 whole square, S minus 1, 1, S minus 1. Now bring it inside, we will get 1 by S minus 1, 0, 1 by S minus 1 whole square, 1 by S minus 1. Okay. Now if we want to find phi t, then we have to take inverse Laplace transform of this. So we will find phi t. So it will come something like e to the power t ut 0 t e to the power t ut e to the power t ut. I'm writing directly. You can solve it here. You will find the same thing. Now what we have to do? We have to find this one, means phi t. This one. Okay, we found. Okay, see what it is the. Let me write it. Si minus A inverse x of 0 minus. Ultimately, we have to bring everything in time domain. So this was in S domain, and say this one. We would have multiplied directly this with our initial conditions, but as now I have found a phi t, so let multiply phi t with our initial conditions, and my initial condition is 1 0. My initial condition is 1 0. I hope it is clear. Don't get confused. Let me delete this. So what we will get? This into this a to the power t ut and t e to the power t ut. So first thing we are getting this. So first part we are getting this. Now see, now we have to calculate this one. Now we have to calculate the second part. Now we have to calculate the second part. So let's see. Let's calculate the second part. So second part also, and here we will keep it in S domain only for simplicity. So what is our Si minus A inverse? It is 1 by S minus 1, 0, 1 by S minus 1, whole square 1 by s minus 1. Then we have b, and then we have 1 by s, that is us. So if we do it, this is 1 by s minus 1, and here we will get something like this 1 by s minus 1 whole square plus 1 by s minus 1. This what we are getting? This we are getting si minus a inverse b us. This we are getting. This we are getting. Now, if we will take inverse Laplace transform of it. Now, if we will take inverse Laplace transform of it, then we will get something like this. E to the power t minus 1. You can do it on your own. You will get the result like this. This you will get this. Okay. This you will get this. See, I told you that if we will bring this in time domain, what we will get? We will get phi t convolve matrix B and ut. So see, in this we brought the STM. We brought this STM into time domain, and then we multiplied it by this because it was simple. Here, try not to bring this part into time domain first. Try to find this whole part. Try to find this whole part in S domain only. From that S domain, apply inverse Laplace transform and then get it in time domain. If we will come in this part, now, then it will become little complex because most of people are not so comfortable with convolution. So why to take the risk? Do it like this way. So we got it here. Now yt we know. Yt, sorry, not yt. First is xt only. x1t, x2t. This we can write it like this: e to the power t ut, e to the power t ut, t e to the power t ut, t e to the power t ut, plus take this e to the power t minus 1 t e to the power t. We will write ut here. So see what we will get. We will get x1t is equal to e to the power t ut, e to the power t ut minus ut, means 2 e to the power t minus 1 ut. See here what we were getting: x1t 2 e to the power t minus 1 ut. So same here also we are getting. By this process also we are getting the same thing. Now if I write x2t, it will be 2t e to the power t ut. Now compare it with this one, x2t 2t e to the power t ut. So these two are our solution of state variables, this one and this one. Now when we will add both, we will get y of t. I am not adding it. We will get the same result as we were getting in the last one. So this is the whole process. This is the whole process. For the solution of state variable, I taught you two method. Method one, where no I taught you two methods. The method one in which no specific knowledge of state space is required. You just have to expand it and you will get x1t, x2t. Then you can apply y of t in this way. In method two, you should know this expression. You should know this expression. You should remember this expression. Then you can solve it partwise. First take this, add it, and then you will get a solution of a state variable. Then you will get the output. Here I told you that when you will convert this into time domain, you will get convolution part. So it is better to solve it in S domain only, and then take inverse Laplace transform. It will be easy for you to solve the equations. So I think this part is clear to you. So I think this part is clear to you. Now see what we saw was x of s. We wrote it as si minus a inverse initial condition plus si minus a inverse b. This equation, this complete equation is called non-homogeneous, is called non-homogeneous equation of state variable. State variable. This equation is called non-homogeneous equation of state variable. Now suppose if we put b, if we put now see, if we put b as 0, so what we will get? This part will get cancelled. This part will get cancelled. So we will get something like this. S of s, si minus a inverse initial condition. Now see, this equation is known as homogeneous equation. Homogeneous equation of state variable. And how we are getting it? If we are putting b is equal to 0 in non-homogeneous equation of state variable, then we get homogeneous equation of state variable. Yeah, we can write it in t domain also. It will be this. We will get something like this. If we want to expand it further, what we will get? We will get x1t, x2t. That is, we will get state variables. We will get stm, and here there will be different initial conditions. So these are all homogeneous equation of state variable. So see, here we have learned a very important thing. This is the solution of state variable. Earlier we told it that it is a solution of a state variable. It is the solution of state variable. It is also known as non-homogeneous equation of state variable. But when we apply b is equal to 0, then we get homogeneous equation of state variable. Then we represented it in time domain, and then we expanded it considering we have two state variables. So I hope this part is clear to you.